form of activity I'll talk about in this very brief flash lecture is ionic activity. And ionic activity is, again, related specifically to non-ideal solutions, okay, where we have no way of making a predictive basis. And, of course, these are going to be for ionic solutions. Sorry, I'm real sloppy in my writing today. So for non-ideal ionic solutions, okay? So I'm just going to present to you the Debye-Huckle equation. So this is called the Debye-Huckle limiting law. Okay? And what this does is calculates the ionic strength. And ionic strength can be, in some ways, a metric for activity for specifically ionic solutions. Okay? And so what really the, ionic strength. And what the ionic strength gives us is really a measure of not only how many ions are in solution, so the higher the ionic strength, the more ions are in solution, but that's also going to create the basis that's going to allow us to calculate the ionic activity. So this equation goes as the following: 1/2 times the sum, and lowercase I is denoting of all species in the solution. Z, this is the charge of the ion in question. So that can be for cations or anions, and that's why it's being squared, so that we don't have to worry about the positive or negative sign. And technically, this is in terms of molalities. So we notice that this is the molality activity. And in the case of aqueous solutions, okay, so what I'll say here, for aqueous solutions, we could make this 1/2 I Zi squared, and we could do this in terms of the molarity. And let's see, for standard aqueous solutions, you know, at 298 K. And the reason for that is because, so we remember that standard molality equals 1 mole per kilogram. Well, this is damn close to 1 mole per liter for water, right? 1 kilogram of water is basically 1 liter of water. It's technically like, you know, 1 liter of water is like 0.9998 kilograms, something like that, right? But reasonably, for these calculations, you can do it in terms of the molarity activity as opposed to the molality activity, okay? So, but now, we still have to be able to calculate the activity coefficient, because I'll remind you that the activity in terms of a solution is equal to this coefficient times mole fraction, or similarly, we could say activity is equal to this gamma times the molarity, okay? And so now from here, there's another equation that becomes part of the Debye-Huckle limiting law, and that says the log of gamma of this activity coefficient equals, and now this is a crazy equation, which it's empirical, so it's based off of data fitting, okay? And so that's negative 0.509 times the absolute value of Z plus times Z minus, so the charge of the cation times the charge of the anion, absolute value, times the square root of the ionic strength divided by 1 plus the square root of the ionic strength, okay? And then so finally, for example, if let's suppose we wanted to be able to calculate some solution property, like perhaps the pH, okay? So up to now, you know that pH is the negative log of the H plus concentration. That's only approximate. You've been lied to. Are you surprised? No, because chemistry is the science of exceptions. technically, the more correct way to calculate pH is the negative log of the H plus activity. So pH, because it's a solution property, and typically it's a solution property of non-ideal solutions, technically pH is the negative log of activity of the H plus ion. And as we'll see, so this limit is best. So these two equations, best for roughly 0.1 molar and less. So when you have solutions that are 0.1 molar and greater, there's some adjustments that are done to these equations, and we're not going to worry about that, okay, in this class.